Okay, so this is our final video in the univariate data section of the course. So that is chapters 1 and 2 in the Cambridge textbook. After this, we start to look at bivariate data, so where we're comparing two variables and looking for relationships, connections, associations, correlations, etc. So the remainder of the data analysis topic will be on bivariate data, but this draws to a conclusion the univariate data. Now I have to say this is a section of the course that I wouldn't give a lot of attention to. It is technically in the course and it's sort of a nice idea, but it's very hard for it to actually be assessed. However, you might be required to, for example, in the data analysis application stack, generate your own set of data, and this is sort of part of what we're going to look at here. So we want to talk about this idea about when we talk about statistics, there's a difference between, statistics for a population versus statistics for a sample. And so a population is a group that we want to know something about, and a sample is a group within that population that you collect the information from. So, if we wanted to know something, something about the population of Australia, we probably wouldn't, it's not practical to survey the entire population of Australia, although I'll talk about that in a second because we do that every 4 years, 5 years, not sure off the top of my head. But what instead we would probably do is try to take a sample of Australians, and we'll talk about the idea of a random sample or a representative sample or all those sorts of things in a minute. We want to take a sample of Australians, survey them, and then try to make inference from that sample to the entire wider population. Now, we don't really go through anything in further maths data analysis that is about trying to make inferences about population. We are really just dealing with what is happening in our particular sample. The statistics covered in maths methods and also in specialist maths looks more at that statistical inference. How do we take what we've learnt from this sample and infer some things about the population from that? Okay, so population, huge group of things that of people or things that you want to know something about, and a sample would be a small subset of that you would collect the information from. So normally a sample is smaller than a population, but the one exception to that is a census. And as I mentioned before, if we wanted to know something about the whole of the population of Australia, I said we probably wouldn't survey the whole population of Australia, but we do that on a regular basis. I'm not sure off the top of my head how frequent it is, maybe every 5 years with a census. Okay, and that's where we literally survey every single person in the country. So the number of members in a sample is called the sample size, and we use lowercase n to refer to the sample size, whereas the number of members in the population is called the population size, and that's referred to as capital N. Collecting data from a population, as I said, is often not practical. Often the main reason is just that the population is too large. As I said, all of Australia, or even all Year 12 students in Australia, might be too large of a population, although that's an accessible population and it's feasible to be able to survey that whole population. But you might not have the means or the finances within your study to do that. You might therefore be trying to just, base it on a sample of students. Another reason we might not be able to collect data from the entire population is that it might be a hard to access population. And I don't mean people that live remotely. I mean something like if you were collecting data to do with blue whales in the Pacific Ocean. Now that's not a population that you are going to be able to access. You are not going to be able to survey or measure or whatever every single blue whale in the Pacific Ocean. Just not practical. And then the third reason we might not be able to collect data from the population is that the data collection process could be destructive. So if we wanted to see what the average battery life is, that would be a destructive testing process. We can't test every single battery to see what its lifespan is, because if we did that we wouldn't have any batteries left. So those are some of the reasons we might work with samples rather than populations. When we talk about, statistics or, trying to describe populations and samples, we refer to the population statistics. We don't refer to those as statistics. They're actually parameters. Population parameters. So the mean of a population is a parameter. The standard deviation of a population is a parameter. Whereas we call them statistics when they're to do with samples. the mean of the sample and the standard deviation of the sample. And we use different notations to refer to these values in the same way we use different notations for the sizes. So in further maths, we're looking at the mean x bar and the standard deviation sx. In maths methods, much later in the year, we look at mean mu and standard deviation sigma. We've already seen in the CAS when we did the one variable statistics, it calculates two different standard deviations, mu, the population standard deviation, and sx, the sample standard deviation. And in further maths, this is the one we want. Okay. All right. So, as I said, we're going to need to take a sample in order to get information about a population, but we want to think about our sample. So a good sample should be representative of the population, and one way to do this is to choose a simple random sample. Okay, it's really important that when you're selecting a random sample, every single person in the population must have an equal chance of being selected. Okay, so if you're going to take a random sample of all Australians and just survey people on the street in Melbourne, not every single Australian has an equal chance of being selected in that sample. Okay, so it's going to be a skewed sample and not representative of the population. So one way to select a random sample is to allocate a number to each member of the population and then use technology to randomly generate a random list of numbers. So for example, you might use mobile phone numbers. Now that pretty much everyone has a mobile phone, you might use mobile phone numbers as a way to sort of have numbered the whole population, randomly generate a sample of 1,000 mobile phone numbers, and therefore pretty much every member of the population is equally likely to be selected. Obviously there'll be some that aren't, but it's very difficult to come up with a completely flawless sampling method. And that's a big part of statistics, actually coming up with the method by which you're going to collect your information and how can you ensure it's reliable as possible and that you can make strong inferences from it. So using a CAS to generate random numbers. So let's say we had a population, we've allocated a number to every member of the population and we want to select some of them. Let's just do a very simple example. Let's say we've got 10 people and we want to choose 3 of them. We give every one of those 10 people a number, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then we can use technology, CAS, a spreadsheet, something like that, or go to a website that will generate random numbers and generate 3 numbers that are between 1 and 10. So the way we're going to do that is we're going to need a new document, which I've already got, and a calculator page, which I've already got, and I'm going to press menu, 5 for probability, 4 for random, and 2 for integer. Integers are whole numbers. So if we want to generate whole numbers, we're going to use the integer generator. And then within this, we need to give it 3 bits of information. The minimum possible integer, the largest possible integer, and the number of random integers that I want to generate. So if I want to generate from the smallest possible integer I can generate is 1, the biggest one is 10, and I want to generate 3 integers, that's what I'm going to type in, and then I'm going to press enter. Okay, so a couple of issues here. If I'm trying to use this as a way to choose 3 people from a sample of 10, this random integer set doesn't help me because I've got 10, 10 and 2. So it's chosen person number 10 twice and then person number 2, so it actually hasn't chosen 3 different people. So I can't get it to randomly generate 3 different integers with my CAS. I'm sure there'd be other programs that you could do that. So a couple of ways around this. You could just do that thing again. So you could just simply do the random integer from 1 to 10 3 times again, until you get a set of 3 that's different. You just keep pressing enter. So I didn't even need to scroll up and get it. If you just keep pressing enter, it'll generate a new set of 3 digits. Keep pressing it until you get 3 different digits. And now I've got 3 different digits. So person number 5, 6 and 8, they'll be my sample. Okay. The other way you could have done it instead was to do, so menu, 5 for probability, 4 for random, 2 for integer. Instead, integers from 1 to 10, just generate the numbers 1 at a time. I just want to generate one integer between 1 and 10. So 1, 4, and 10 are my 3 integers. And again, if I got a repeat, I'd just go again until I got something different. Okay, one thing I just want to note before we do this is you might notice that when I generated 3 integers between 1 and 10, I got exactly the same 3 integers as what I did in the screenshot in the notes over here. And you will find, if you do it as well, and I'd like you to do it, that you will in all likelihood, unless perhaps you're using the CAS of an older brother who's done further maths before, or something like that, you will probably have got the same two sets of 3 integers as I did. And that's a bit of an issue with CADs or any random number generator. Okay, and that's because it can't be completely random. A computer can't be completely random. It can be programmed to be random, but it has to be random from a fixed starting point. And so all your CASs by default in their factory settings have the same fixed starting point. I don't know what it is. Maybe it's just number 1 or 0 or something. But they're starting from the same value when they're running their random program. Okay, and so in fact it doesn't generate random things. We end up with the same patterns. That starting point is called the seed value. And what we need to do to ensure that our technology can generate genuinely random sets is to choose a random seed value. Okay, so to adjust the seed value, as I said, sorry, it does say here, the CAS's default seed value is 0. Okay, so in order to change the seed value so that your CAS does its own thing, which is what you want it to do, you're going to press menu. So I'm looking here in the notes, menu, 5 for probability, 4 for random, and 6 for seed. Oh, sorry, I need to be on a new entry line. So menu, 5, 4, 6, and then I'm just going to type any number. You might type your mobile phone number. You might type just your favourite number. It shouldn't just be a one-digit number. You know, it's only really 10 one-digit numbers. It's not going to be particularly random. You might just press numbers randomly on your keypad and press enter. Okay, so there's my seed value. And now when I do menu 5 for probability, 4 for random, 2 for integer, and between 1 and 10 choose 3 integers, if you've all done your own seeding, we should all now get a different set of 3 integers. Okay. If I were to seed it back to 0, menu, what was it, 5, 4, 6, I haven't done this, I'm testing this. If I seed it back to 0 and randomly generate 3 integers again get that 10, 10, 2 and 6, 5, 8. Okay, so randomly seed your CAS to something you completely made up, and then you're good to go in terms of being able to genuinely generate random integers that are going to be different from those of the person next to you, which is what we want. Okay, let's work through an example. So this table below, which I've copied out of your textbook, it shows a population of 50 people and their IQ scores. And it's actually also colour-coded to try and indicate male and female, slightly stereotypical, the male's in blue and the female's in red. So you could use this particular data set provided in your book to play around with different sort of variables, whether that's a categorical variable in gender or a numerical variable such as IQ. Okay, what we're going to do is we're going to select a random sample of 10 people by using my CAS to generate 10 numbers between 0 and 49 inclusive. So we can see that each of these people have been given a number from 0 up to 49 to identify them. So I want to choose 10 people. Now I could do this in 2 ways. I could do menu 5, 4, 2, generate a random integer from 0 to 49, and I could generate 10 straight away. But it's probably unlikely you're going to get 10 different numbers. Oh, it looks like I might have got 10 different numbers. Anyway, the other way you could do it is to just generate one integer, do it 10 times, and if you get any repeats, just do an 11th one. Okay, I think I do have 10 different integers there. Let me write them down over here. I'm going to try and write them in order, just so I've got an ordered list that will help me. So I think 9 is the smallest one. Then 19. Now I would like you to do this separately yourself, so why don't you generate your own set of 10 random integers, and then we can follow along with the same problem. Perhaps pause the video, work your way through the problem, and then you can come and watch me work my way through my set of integers. Or you could watch me work through this and then go back and do it yourself with your own set of integers to check that you can do it. Okay, so I've got 9, sorry, not 19, 18 is the next one. 9, 18, 19, can't cross it off on the CAS, which I like better to do. Okay, I think they're all the teens. Anything in the 20s? Just the 27? Okay, anything in the 30s? We've got the 38, 35 and 37. So in order that's 35, 37 and 38. And then 37, 38. And then in the 40s, we've got 41, 43, and 47, I think. 41, 43, 47. Let me just check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, good. So those are my people. Let me highlight them. So my people are person number 9, person number 18, person number 19, 27, 35, 37, 38, 41, 43, and 47. Okay, so those are my people. So part A, select a random sample of 10 people by using your CAS to generate 10 random numbers between 0 and 49. Write a list of the 10 IQs from your random sample. Okay, sorry, so I'm going to get rid of my numbers there now that I've highlighted my people, and I want to write down their IQs. So we've got IQ of 100, IQ of 117, IQ of 89, IQ of 120, IQ of 116, IQ of 126, IQ of 108, 109, 12, and 97. Okay, so there's my IQs for my 10 people. Your list might look different. Part B, I want to create a stem plot to display my sample. Okay, so in order to make a stem plot, it's easier if I order the data first. So I'm just going to do that. 89, 90, oh sorry, 97, 108 and 9, I think. No, 100, 108, 109. Let me cross out what I've done. 89, 97, 100, 108, 109. Then we've got 112, 116, 117, 120, and 126. Let's check I've still got 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep, good. Okay, there's my list of data. So thinking about my stems need to go from 8 up to 12. So 8, 9, 10, 11, 12. And then I can add my data to the stem plot. Again, making sure that we keep our data values, our leaves, lined up in nice neat columns. Might help you to rule yourself some pencil lines along these lines. Okay. So 89, 97, 100, 108, 109, 112, 116, 117, 120, 126. Okay, so there's my stem plot. I need a key. So I'm going to say 8/9 means IQ score of 89. Okay, and then part C, we want to create a box plot to display our sample. So we're going to need our 5-number summary. So the min and max are highlighted in yellow. And then we've got 10 bits of data, so the median will be between the 5th and the 6th. 1, 2, 3, 4, 5. So the median is going to be halfway between 109 and 112. We can work that out by averaging, if we're not comfortable with that, sorry. So 109 plus 112 and divide by 2. Control Enter. So that's 110.5 for my median. My lower quartile says 5 bits of data in the first half, so the middle value is the third one. 5 bits of data in the second, so the third one after the median is Q1 and Q3. Okay, so our 5-number summary is clear from up there. So our data needs to go from 89 to 126. So we want to scale. Maybe we want to go from 90, 100, 110, 120, 130, so that'll be 95, 105, 115, 125. And then we can okay, so we've got everything we need. Oh, we do need to go from 89 though, so let's go back here a bit. Okay, so our minimum value is, we do need to check for outliers. So our IQR is 117 minus 100, so that's 17. Lower fence is going to be Q1, which is 100 minus 1.5 times our interquartile range. 100 minus 1.5 times 17 is 74.5, so no outliers at the bottom. Upper fence is going to be upper quartile 117 plus 1.5 times the interquartile range. 1.5 times 17, 117 plus 1.5 times 17, 142.5. So don't have any outliers. Do need to check that though. And your data set that you randomly generated might have outliers, so it might be different to mine. Okay, so I can just mark in my points. So there's 89 for my minimum. Q1 is at 100. Use a ruler. Median is at 110.5. Q3 is 117. And max is 126. Okay, join up my three middle values to make the box, extend lines out to my whiskers, and there's my completed box plot for the data. So I think we can see from both the stem plot, if we would turn it to its side to see the histogram, and from the box plot that it's roughly symmetric, but maybe with slight negative skew, the distribution that I've ended up with. Again, yours could look different. Okay, other things to think about would be situations where you might want to randomly allocate a sample of people to groups, and we could again use a random number generator to do that. So if we had 3 different groups to allocate people to, we could use our random number generator, menu, 5 for probability, 4 for random, random integer, generate an integer from 1 to 3, from 1 to 3, and we just want to generate one integer. Okay, so the first person who walks in the door goes into group 3, the next person goes into group 1, the next person goes into group 2, the next person goes into group 3, the next person goes into group 3. Now, if you just did this completely randomly, you could end up with really uneven groups. So if you wanted 3 equally sized groups, you would need to work out how many people you're going to have in each group. And then once you hit the limit, so then maybe you've maxed out group 3, it's reached its limit. So then you could continue to allocate randomly just between groups 1 and 2 until you've got the next group filled, and then everyone else goes into group 1 or something like that. So different ways to randomly organise people. You could also use a coin if you're dividing into 2 groups, or a die, but again, you just might have to think about a way to deal with the fact you might need same size groups. The last thing is to just know that your CAS can also generate a sample of normally distributed data, and that may well be what was used to create the IQ data in this table up here, for example. So if I want to generate a random set of IQ data, I'm going to go to menu, again, 5 for probability, 4 for random, this time normal, 4 for normal. And I'm going to, so within the brackets I need to enter the mean, the standard deviation, and the number of random integers that I want to generate. So let's say I want a mean of 100, which is IQ, a standard deviation of 15, and I want to generate 50 values, then I can get my CAS to do that for me. Now, they won't be integer values, they're going to be decimal values here, so you might then choose to round them to get to give the 50 IQ values that you need for your table or for your data set. Okay, it is possible to simply add that data into a lists and spreadsheets page to be able to then do things with it, and you can do that by storing your data list. So see how it's put my list in these curly brackets. If I now press store, which is Control var, and I'm going to store this list, so the previous answer, as something, I'm going to store it as IQ because they're IQ scores. Then if I now it's stored. Now if I go into a lists and spreadsheets page, so Control I, insert a new page, number 4, lists and spreadsheets, up the top here, if I type IQ, a variable IQ, press enter, it'll populate that column with the lists and spreadsheets data. And so then I should be able to do my one variable statistics, menu 1, get out of there, I need to be actually in the data I think, menu 4, 1, 1 for my one variable statistics. I've got one list, it is in column A, or I can refer to it as being IQ, same thing. And it will do my statistics, and we should find here, my standard deviation is not 15. What's my mean? My mean is about 100. My standard deviation is only about 10 though. Go back over here, did I type the wrong thing in? No, I suspect it's really just because it's not that big a sample. If I generated a sample of 1,000 bits of data or 10,000 bits of data, the standard deviation would likely be more accurate. It's not a big enough sample to ensure it. But yeah, so you can generate a data set with particular properties. Look, realistically, you're not going to need to generate a set of normally distributed data, nor will you need to randomly allocate to groups. You might need to randomly generate a list of data. As I said, more likely perhaps in your SAC on this topic than or an assignment, rather than in the actual exam. So not a particularly key section of the course to be worrying too much about. The exercise here is exercise 2I. I've listed Appendix A because it's actually not in the textbook, it's not printed in the textbook. Perhaps in your current version it might be, but it's a separate exercise available online, and so I've attached it in your topic booklet for you to access there.